Okay, well, thank you very much, Carol. When I came here, I wasn't quite sure how much of the information I was going to present is relevant to this region, but listening to Kurt this just a few months ago, I think quite a bit of the things that we're seeing in Montana are consistent with what you see over here and vice versa. Soil acidification in Montana is a new phenomenon, and that's maybe a little different than the history over in the Palouse, where you've had the problem going on for several decades. It's just recently appeared. This title slide I have here is a picture from the Highwood Bench, which is east of Great Falls, Montana. And it's an area where the field of barley with a pH of about 4.4. And obvious symptoms or severe symptoms of aluminum toxicity in this field. This photograph was taken back in June 2015. And a number of people were involved in identifying what the problem was, because at the time no one knew what was going on with some of the fields in this county, and it was identified that the problem was related to low pH and aluminum toxicity. And this was really startling because there was no history of this in Montana. My background is I've been with Montana State University now since 1983, about 37 years, and historically never had this problem. And when I first started working at Montana, I never thought this problem would start to occur in Montana. But anyways, we're starting to see problems develop, but it's, again, an emerging issue. And what I want to do this morning is just visit with you about some of the experiences I've had in the state and some of the challenges I see to efforts to remediate our acid-affected soils. So, causes of the acidification. The big issue that I always talk about in my talks to producers is looking at fertilizer nitrogen consumption. When I first began working in Montana back in the early 80s, actually 1983, our consumption was maybe 1/3 of what it is today. And thereafter, and as you can see from the graph, or from this chart, fertilizer nitrogen use has grown tremendously in Montana. Now, right now we're kind of in a mature market, but looking at the consumption over the last few decades, or even more than the last few decades, you can see a steep rise in fertilizer nitrogen use. Right now, nitrogen is being applied really as urea. It's actually like 86% of the nitrogen that goes on in soils is applied as granular urea. And that urea is most often applied as a broadcast application. There's not a lot of banding going on. Some farmers do that, but still it's dominated by broadcast applications to the surface. So when I talk about causes of acidification, then it's really the increase in nitrogen consumption. And as I mentioned previously, historically, low pH was not an issue, but then again around 2015, farmers in selected areas of the state, particularly on the Highwood Bench in Chouteau County, started finding problems related to stands and production of cereal grains, and a number of factors were considered, and it became evident that low pH was the problem and elevated extractable aluminum levels. And again, that picture I showed in the title slide was from the Highwood Bench area. So again, I mentioned that if you look at the big picture in Montana, low pH is not a big issue. And I think it's fair to characterize it as an emerging issue. And depending on your point of view, I guess we're way behind Palouse area in that regard, but that maybe is a good thing. But there are selected counties, in particular Chouteau County, where we see a lot more low pH soils. And when I talk about low pH, I'm talking about pHs less than 5.5. And in Chouteau County, we find a lot of samples that are coming in that are even less than 5 or even down in the low 4s. So it's an emerging issue. We have 23 counties now. Clayne Jones, my colleague on this project, put together this chart where we have at least one field that was identified with a pH less than 5.5. And this is interesting because when I started working in Montana, probably we wouldn't find more than 1 or 2 counties with this situation. But again, our work is centered in Chouteau County because that has been kind of a focal point of soil acidity problems in Montana. And that's that county right there I've circled. And there's some reasons why that county has been focused on, well, other than the problems there. But one of the things about Chouteau County that's interesting, it's got the Highwood Mountains going through it. It's in the, let me see if I can get this pointer to work, southern part of this county here, east of Great Falls. Those are the Highwoods. And that area around there and has considerably higher rainfall than some of the other areas in the dryland Montana. You're talking maybe 15, 16 inches of precipitation versus other areas in eastern Montana, which are maybe 12, 14 inches. Because of that, there's a lot more recropping going on. Fertilizer nitrogen inputs are also greater because of the annual cropping. Also, there's this phenomenon of saline seep control. There are a lot of saline seeps in Chouteau County, and one of the approaches that has been used to remediate or to deal with the saline seep problem is to annual crop. Well, you annual crop things like grains, more nitrogen inputs. And so that's one of the issues going on. Also, there's an area up in the northern part of the county next to the town of Big Sandy, which has a lot of sandy soils. But that's somewhat unique to Montana. Most of the soils in Montana are actually fairly fine textured soils. So just some of the reasons why we think the problem is showing up first in Chouteau County. And my thought is that Chouteau County maybe is kind of the canary in the coal mine type of county for the rest of the state. I do see some problems developing in the future in other counties, particularly in the northeast part of the state. So what I want to talk about then is some of my surveys that I've done of farm fields in Chouteau County. I'll talk about some of the results from on-farm sugar beet lime trials, and then just talk about some studies we've done with phosphorus fertilizer. This is not the only components of the study, but just a few things that I want to visit with you about this morning. One of the first things I did, and I got involved in this project in 2016, was to do a survey of fields in Chouteau County and where we saw aluminum toxicity problems. And one of the things that was really evident, and I'm sure is evident in this part of the region, is the pH stratification effect. The problems with acidity are confined near the surface. But one thing that is different in Montana than maybe Palouse is our lowest pHs are right at the surface. And so closer to the surface, the lower the pH. And again, most of the nitrogen goes on as a broadcast nitrogen application. So that part of the situation is maybe explainable. We're not deep banding the fertilizer nitrogen. And if you look at some of these 5-farm survey where I saw aluminum toxicity, the pHs are maybe 4.5, 4 near the surface, and then you go down with depth, say 15 centimeters, your alkaline situation. So the lowest pH is likely found in the shallowest depths, and that's again because the nitrogen is applied near the surface. We also have no-till, and I don't like to blame no-till for the problem, but it has maybe aggravated things a little bit in that we don't get the mixing that goes on with tillage, and so some of the stratification is maybe a little more intense under a no-till situation. Also, with depth, a lot more carbonates with depth. It's true of our soils, and I'm sure it's probably true out here. And so there's a lot more buffering capacity going on. So it's not surprising then that the pH is quite high with depth. Okay, so let's move on. Kurt talked about spatial variances in the field, and that was one of the things that was really stark to me. And I think he used that word, patchiness is what you used. We have patchiness too. And I once had a grad student, there was a grad student apartment. I remember she gave a seminar and she said, the world is a patchy place. And she's talking about communities of plants in rangeland situations. Well, that is also applicable to some of the soil pH situations we have. The spatial variances in the fields can be tremendous. This is an example of a winterwood field on the Highwood bench. Whoops, let me back up. There's the Highwood Mountains, where you have aluminum toxicity. The pH is 3.8, and just go a few feet away for no rhyme or reason. Maybe pH is 5.1. The wheat seems to be growing quite normally. Kurt said there wasn't really any pattern to some of the pH variances in the field. And I think that's maybe true in some parts of the state, but in Chouteau County, for some reason, we're finding our lowest pHs typically being found in low-lying areas or depressional areas. And just another example here were the variances. This is a lower-lying slope position. pH is 4, and up here it's 6. One of the other interesting things, and here's what it looks like more at a field landscape scale. Typically, at least in Chouteau County, we find lower pHs in the bottom slope positions. You get to the summit slope positions, the pH is higher. It may be because of the erosion which has occurred over time and the more prevalence of carbonates near the surface. Now, here's another example. I talked a little bit more about saline seeps, and this is a pretty wild situation, a field I surveyed. So you've got this one area down here with saline seeps showing up. This is an image on Google Earth. And then you go to another end of the field or adjacent field. You got pHs in this area were like 3.8, and there was aluminum toxicity going on. And then some areas over here, pH 5. So it's kind of crazy. You can have some fields where you have saline seeps at one end of the field, and the other end of the field, you have aluminum toxicity. So it's a pretty wild situation. And what it really means is, and the reason why I bring it up, when we talk about soil sampling efforts for aluminum toxicity identification, they really need to be localized. You need to go to where the growth is poor, sample just those areas of the field, and then also because of that pH stratification effect, we need to be mindful of what depth we're sampling at. Traditionally, we'll sample, let's say, the top 6 inches. Well, probably is a good idea to break out that top 6-inch layer into a 0 to 3 or 3 to 6-inch layer if you really want to find or diagnose the source of a problem. And again, most of our problems we're finding where we get pH less than 5 or even less than 4.5. So I want to talk about some of my on-farm sugar beet lime trials, and I see that as my remediation component in this study. There's been a lot of interest and even use of sugar beet lime in Chouteau County. And so sugar beet lime, it's just a byproduct of the juice purification process. It's generated by heating rock quarry lime, calcium carbonate limestone in a kiln to temperatures in excess of 2,000 degrees Fahrenheit. That extreme heat results in production of calcium oxide and CO2, which is then injected to raw juice. The calcium oxide binds about everything in the raw juice except the sucrose, and then the calcium oxide then reacts with CO2 to form calcium carbonate precipitate. So it's that calcium carbonate precipitate that is going on these fields. So the sugar beet lime source for Chouteau County is the Western Sugar Beet Company in Billings, Montana. And we did some experiments with that at 3 farm sites on this project. That material contains a lot of water. That's one of the nasty things about it. It's about 30% water, and so it's kind of clumpy. Also has a fair amount of organic matter, but it does have a lot of calcium carbonate in it, about 75 to 80% on a dry weight basis. But really, if you start looking at calcium carbonate equivalents, because of the water, it's only like 55% calcium carbonate. The good news with sugar beet lime is that it's free, but I guess the bad news is you got to go haul it, and so there's cost involved in hauling that material. This is what we did in this study. We hauled this to our field sites. This was done in October 2017 or the fall of 2017, and the cost in shipping the material, and it's done in these semis, is about $35 per ton. It's then loaded onto this, what we call the Stoltzfus wet lime applicator, and then spread out in the field. And the farmers we were cooperated with on this project were all actively involved in this. They loaded the material. I bought the material for them, and they loaded it up on this wet lime applicator and spread it on the field. So what I want to do then is just tell you about some of the results and show you some pictures from those trials. Again, we had 3 farms in Chouteau County: Big Sandy, Fort Benton, and North Geraldine. Grower cooperation with the application of lime. And then there was incorporation with tillage at 2 farms and 1 without. And so the 2 farms, Fort Benton and North Geraldine, material was incorporated with tillage. And in 1 farm case, it was not. A lot of farmers are kind of facing the question, okay, can I remediate pH without incorporating? And so I've got some work going on with that, and I've got a couple pictures I'll share with you. But anyways, these strips in the field, at least some of them are replicated. The 0 and the 4-ton sugar beet lime rate are replicated 3 times, and then I have a 2 and a 6-ton rate, or actually that 6 is actually a 1-ton rate at one of the locations. So I want to share with you some of the results then. And so Kurt was mentioning about lentils. And so lo and behold, in 2018, one of the growers decided to seed the field where he had the sugar beet lime strips to lentils. And I was kind of blown away early in the season when I saw these stark differences in just the growth and, the lack of better words, about a biomass, the vigor of the plants in May. And this picture was taken in May. This is our unlimed area. This is our 4-ton rate. And those are our 4-ton rates. Easy to pick them out. You'll see this green area here. You're wondering what that is. Those are weeds. But this is one of the things we saw at our trials. Big differences, at least with the lentils, in terms of the vigor of the plants. Taken a few weeks later, looked at biomass. There were some obvious differences in biomass in the unlimed and the limed areas, but as was often the case in Montana, just because you generate a lot of biomass doesn't mean it translates into yield, and when it came time for the yield, it was kind of a wash. So we saw we saw great differences in growth and vigor of the plants with the lime in the case of lentils, but not in terms of the final yield. Okay, just want to show you the results from the yellow peas. This is at another farm site. Carol, how am I doing for time here? Thank you. When do I have till again? 11:50? Oh, okay, it's right. I'm an hour ahead on my clock. I moved my clock. I'm okay. I was getting worried. I forgot to move my clock back. This is another farm site, and it was taken this last year. It's yellow peas, and again, our 4-ton rate on the left, the unlimed area on the right. Obvious differences in growth. Little pictures taken a little later on. You'll see there's a difference in nitrogen content. And so what we're kind of deducing is that there's an effect of the liming on the rhizobial activity. And I think Kurt mentioned that in the previous slide. So it's nice to see similar results from adjacent regions. I dug out some plants from that study, and you can see this is from our limed area, a lot of nodules where we put the lime versus not so many nodules where we did not apply the lime. So that was really obvious, and that was, again, reflected in the nitrogen content. And then if you look at yield, this is a case where we did see a very good response to the yellow peas to the lime applications. So we went from 30 with lime to our base yield was like 23 bushels per acre, so 7 bushel yield response. So that was kind of promising. We have run cereal grains on these same sites and have not seen yield responses to them, though we have seen differences in terms of the early in the season in terms of how green the tissue was. And in this case, it was because the cereals followed the lentils, and we think there was a residual effect from the amount of nitrogen fixed by those lentils. Okay, so what I want to talk a little bit is about some of the soil sampling efforts we did at these field sites. And I've got all these little asterisks here, and these are GPS reference sampling locations. And what I've been very careful to do in our study is go into each one of those strips to find 6 to 8 locations with each strip that is GPS referenced. And I've looked at the changes in pH before and after the lime application. And it's important, I thought, to do this referencing of these GPS locations because, as our data has shown and Kurt's has shown, a lot of natural variances in the field. And if you just go willy-nilly through a strip and don't sample the same locations, you know, at the start of the experiment or 2 years down the road, you could get kind of a wrong picture of what's going on. So this is what we did. And I want to show you some results here. We collected composite cores around each one of these stars, 0 to 2, 2 to 4, 4 to 6, and 6 to 8. So we went down to 8 inches, and we divided the cores up into 4 different depth segments. So this is the results from 2 of the locations, and the 2 locations I have here is where the beet line was incorporated. And this is what we saw. Okay, so what we have here is soil pH change from 2017 at 1 year and 2 years post-application of the sugar beet lime. And so what was good at the 2 locations, they both responded similarly to the lime applications. Obviously, there was a difference in year. From the year, we got a little bit higher pHs 2 years down the road versus 1 year post-lime application. And I'm surmising that some of that lime was still unreacted 1 year post-application. But similar response at both locations. And if you look at what it would take to remediate those soils, and bear in mind, one site, the base pH is about 4.6 without lime. The other case, it's about 4.8. So let's just call it 4.7. If we want to bring the pH to what? 6, we got to change the pH 1.3 units. That's over here. And so we need about 2.5 tons of this sugar beet lime. But bear in mind that sugar beet lime is only 55% calcium carbonate. But the point I'm trying to make from all this, it takes a lot of sugar beet lime or any lime material to change pH. And in this case, where target pH is 1.6. And that's equivalent to about, the 2.5 tons is equivalent to about 1.4 tons of calcium carbonate. And I think my numbers, I looked at, what was it? Tim, I remember you had that Pendleton site. I thought it was interesting that I think you got a similar pH change that what I observed at that same lime application rate. But anyways, one of the challenges I've seen or we've come into is that because of all the direct seeding going on, growers want to know, can I just apply some pelleted lime with the seed and correct the problem? And the answer I try to tell them is no. This really, what you have to do, and the way growers have to view this is that we're not just fertilizing the plant, we're really trying to change the properties of the soil. It's really, when I talk about remediating pH, it's really, truly a remediation effort. And it has to be viewed in that context. And so it takes, the thing I want to emphasize is that, and the challenge is try to communicate with growers, is it's really a remediation effort, and it takes a lot of material, liming material, to change pH. And it's things like adding 200 to 300 pounds of seed-placed lime per acre per year. It's going to take a long time to really correct the problem. The other issue is the issue of tillage. So I mentioned we had 2 sites with tillage and 1 without. So this is the depth profile at the locations with tillage. We got our biggest differences in the top 2 inches. And remember, these are actually average of 0 to 2 inch depth, or the 2 inch depth profile at North Geraldine. And we saw differences in pH down to that top 4 inches. The samples down below 4 inches, 4 to 6 and 6 to 8 were not affected, which is not surprising. But basically that pH stratification effect with tillage, we were able to eliminate it. And so this is, again, the picture at Fort Benton and North Geraldine, 2 years down the road. This, I've just shown you the 4-ton rate, which is about, what, 2.2 tons of calcium carbonate, or 2.3. The point I'm trying to make here is the lime does, okay, and then I want to compare it. Big Sandy, this is where we did not add any, there was no tillage. The surface pH was the only thing that was affected. And even this number here is probably kind of bogus, because when I went out and visited the site, there's still a lot of lime material still evident at the surface. And so you stick a probe in the ground, even if you only go 2 inches, you're mixing that, how do I say, unreacted lime with soil, and then you mix it in the lab, and you get kind of a bogus pH reading. I guess the point I'm trying to make is we really need tillage to correct the problem. And the point I want to make is that lime does not really wash or leach into the soil profile very easily. And without tillage, pH remediation will be, at least to me, confined like to the surface. it would take a long time to see changes going on. I realize I only have a 2-year time window, but my instincts tell me, and I try to tell growers, is that if you got a problem, fix the problem and get it over with. That's kind of where I'm trying to go with, or that's the approach I'm trying to go with in my talks to growers. So let's move along. This is a picture of that field. Oh, good, we're getting there. With the aluminum toxicity in safflower. This is a field where there was no tillage. And this is the worst case of aluminum toxicity I've seen in the state. We set up our sugar beet lime experiments here. And I'll just show you, there was no effect. Without tillage, there was no effect of lime on the safflower. And those are what the safflower plants look like with the aluminum toxicity. The roots are necrotic and they have this J-shaped effect. So the other thing about single tillage event, one of the questions or issues that's come up is, well, I can't till my soil because I'll destroy organic matter. And we've looked at that in some of our studies. And suffice it to say, a single tillage event does not destroy soil organic matter. And so what we did is we went to those field sites. I looked at the soil carbon levels before and after the tillage event, and they follow this one-to-one line very nicely. If there was a destruction in organic matter with tillage, you would expect to see a lot of points down in this area down here. And this effect is consistent with long-term studies in Wyoming and Saskatchewan, that a single tillage event is not problematic in terms of soil organic carbon. Here's an average numbers that we got then, 0 to 2, before and after tillage. They're about the same. There's really no evidence that we're destroying organic matter with that single tillage event. Sugar beet lime remediation costs, I'm going to kind of skip over that a little bit because I've gone over my, well, let me just mention a couple of things. One of the things, let's see. Okay, we've looked at how quickly soil acidification occurs, and we've done this by looking at results from these long-term cropping system studies. And this is a study that we had at our MSU post farm. It's an Amsterdam silt loam soil without calcium carbonates. And what we found is, and this is like over 14 years, and we've looked at the changes in pH over these suite of different cropping systems, CRP, some with tillage, some with different just levels of nitrogen. And what we found is that there's a correlation between soil pH after 14 years in the 0 to 4 inch depth and cumulative nitrogen inputs. And the slope of the line says that 100 pounds of N is going to drop the pH about 0.04 units. So it's going to take 23 years to drop pH 1 unit if we were applying 100 pounds of N per acre. And the reason why that's important is I want to emphasize to growers that this soil acidification process, it occurs, but it's a slow process, and it's not going to happen all in 1 year. And so, when we start talking about economics, like what Kurt was talking about, we need to look at, if we remediate the soil to say pH 6, that's going to be a big investment, maybe $100, $150 per acre. But if you amortize those costs or look at a capital cost, it's not so bad, particularly over like 15 years. If that's how long the lime application lasted, it would be like $6, $7 an acre. And again, that's consistent with studies in Saskatchewan and in Saskatchewan. Okay, so let me talk about my phosphorus work because I know Carol definitely wants to see that. And so we got interested in seed-place phosphorus in some of our studies because some work in Oklahoma which had shown that by adding phosphorus with the seed, you can remediate aluminum toxicity. So this is a field site in Oklahoma I got from Chouteau just recently. It shows first that the site is very responsive to lime, but notice, and here's the next slide, excuse me, he put triple superphosphate, he got a similar effect from the lime. And so I knew about this study, and work had been done in Oklahoma. Some of it dates back to the 1990s. So I tried it in Montana. And so here's a site that we did where we had phosphorus and lime applied to durum. So we had a lime strip here, an unlimed strip here, and then we had different phosphorus rates. First thing you'll notice is the pH is 4.4 without lime. Aluminum toxicity symptoms showing up. With lime, symptoms go away, the growth is much better. This is in durum, and this is on the Highwood bench. So we also looked then at phosphorus, and we found that phosphorus mitigated aluminum toxicity. And here's the 0 and the 90 rate. And this was interesting. And the thing I want you to bear in mind is the phosphorus test at the site was very high. The Olsen P was like 50 parts per million. It was extremely high. So we saw a big response to phosphorus fertilizer, even though the soil tested high in P. And this is identical to what they've shown in Oklahoma. This is a picture of the same plots near maturity. And you can see differences in growth. And I've got the yield data here. So were we limed? No response to phosphorus. That's the green up here. This is yield, phosphorus rate. Look what happened when we added phosphorus fertilizer. You add about 60 units of P2O5, and your yield approaches what it does in the limed area. So, and again, this soil acidity effect resulted in a 50% yield loss relative to the ag lime. That is 22 versus 45, or 23 versus 46. But with phosphorus, we were able to achieve a high yield potential similar to where we had lime. The conclusion is that phosphorus fertilizer may be a short-term solution. However, it's not remediation. And this is consistent with Kansas studies. And again, this phosphorus was placed with the seed. So that was in two years ago. We saw a similar effect in 2019 in terms of the crop growth, but this field site got hammered by hail. And so I looked at biomass, and we kind of saw the same thing. So where this situation might be applicable is, I know a lot of farmland is being leased, short-term lease agreement. Person doesn't want to invest, the $100, $150 for lime remediation. This might be a short-term solution. But again, it's not remediation. It's more or less living with the problem. Why does that seed-place phosphorus work? The literature is actually a little confusing. People have noted that adding phosphorus to soil will precipitate aluminum, but the problem is if you're seed placing phosphorus, you're not hitting the whole soil matrix. And so what the thought is that when you get high concentrations of phosphorus absorbed by the roots, that aluminum precipitates in the roots and makes it less toxic. And so there's been a number of studies that have looked at that, and that's kind of like the prevailing mechanism why that seed-placed phosphorus seems to work. So just summary, this is my last thing. Take-home messages. Montana croplands are becoming more acidic, and I've said nitrogen fertilizers are really the big reason. I showed you that slide with 3x nitrogen consumption increase since the mid-'80s. No-till may have contributed to the pH stratification in the surface, but it's really, to me, not the big issue. Chouteau County surveys revealed large gradients in pH with terrain, topography changes, and topography. And I guess I want to emphasize that soil sampling to identify a problem needs to be localized. Aluminum toxicity systems, like in the Palouse, we see them at pHs less than 5. Frequently, it has to get down even lower than that. Nitrogen fixation and nodulation, responses to lime applications have been observed in our pulses, and that's probably even more prevalent than the aluminum toxicity because nitrogen fixation will be impacted as the pH drops below 6. So the final thing is that management options exist to cope or adapt to this problem. Seed-placed phosphorus, obviously looking at aluminum-tolerant genotypes, but ultimately to me, and because I'm a soils person, I insist that liming is the only way to remediate soil acidity problems. And since we had all sorts of presentations about soil health, I'm sticking with that importance of liming. That to me is what we've got to do. So thank you very much. Okay.
I thought in Montana you had old seed beds there where you would have calcium carbonate available to lime.
Not really. I mean, I don't know how you would get it to the fields. I mean, there's calcium, there's obviously saline seeps and things like that, or there's calcium soils with calcium carbonate right at the surface, but that would be a little bit difficult, I think, to remediate soil pH, even with the patchiness issue. I think it just, growers have gone to these sugar beet lime, and so, at least in the Chouteau County.
That's the cheapest source you have.
That's right now, well, it's free, but then there's the transport. But they're looking at other materials too. There's some kiln lime that some people are considering out of Helena, or not too, just south of Helena, near Townsend. And any other? Okay, right over.
Can you please clarify in your talk, and maybe this can go to Kurt too, since we didn't have time to answer questions for you. Is this a single application or annual application to see these long-term effects of the lime per acre? And it also, I guess the second follow-up to that would be, there's the standard practices of applying the fertilizer continuing, and you're still seeing these positive effects.
Okay,
so
I think
if you're putting the lime on and you're continuing to do the fertilizer application, are you still seeing that working and being effective, or
all right,
are you
so
continuing to degrade it?
Okay, so let me try to. First thing was a single application. We're not talking about annual. We're talking about one time over maybe a 15, 20 year life cycle. You remediate pH. That pH is still pretty stable, okay? It's dropping obviously with nitrogen inputs, but I tried to get with that one graph and I spent too much time talking about the other ones. pH isn't dropping, 1 unit in 1 year. At least what we found out that one study was it would take like 23 years to drop pH 1 unit if you applied 100 units of N. So I think the thing to bear in mind is that a lime application, it's got a long-term effect, and so it's best to look at it as what, a capital cost, Kurt? Is that how you? That's how we look at it. That's how I want people to look at it. Okay, it's a big mouthful first time around, but if it's a long-term thing, then it's fine. The other issue we had was about practices. Yeah, I know you were the one who asked about the pulses. Yeah, and to me, inclusion of pulses in rotations is one way to reduce those nitrogen inputs, because it all ties back to nitrogen inputs to me. That's the big issue. And by including the pulses, we're not fertilizing nitrogen, we can mitigate just how quickly the pH is falling. So to me, that's one of the solutions to long-term, assuming once the pH has been remediated. But even where problems are developing or potentially could develop, the situation is prolonged by having pulses introduced.
I guess I'd agree with that. My studies as well, I've been just using a one-time higher rate of lime application. The concern with doing piecemeal over time and small rates, I mean, I get that. It's more cost-effective per year when you think about it up front. When you look at these annualized costs, I actually think it's cheaper over time. And the other issue, if you're putting down small incremental amounts, it may be a decade before you actually start seeing high enough improvements in the pH of the soil to start seeing an economic return on your crops. If you're putting down 200, 400, 500 pounds, it's, in my experience, that's not enough to see a significant increase in pH and a yield improvement. So you're spending money but not getting that immediate return. If you put down enough lime to remediate that soil to get it back up to the pH of 6 or higher, you're going to see an immediate return in your crop performance that first year, and so you can start paying for that lime.
Yeah, let me chime in too. People have looked at like that 200-300 pound rate in Oklahoma, and there's no effect. And maybe it's because I'm getting a little older and crustier. It's just, I say, if you got a problem, you fix the problem and you get it over with and you move on. And that's the way I look at it. That's.
Can I piggyback on that real quick? It's something that I've thought about with soil acidity and liming. So if you're gonna put down a lot and kind of commit to getting soil pH above 6 or whatever your target pH is, you don't necessarily have to do it to the whole farm all at once. Something I've thought about is maybe the approach of rotating your lime application around your farm. Maybe hit your worst spot first and then kind of work around from there. So maybe Kurt has one.
Let me chime in there too, because that title slide I showed you with that picture of those acid effective fields on the highwood bench, that farmer there, the owner, has just done that kind of piecemeal. He's done it over 5 years. He doesn't really have a problem anymore. And he'll take one field, takes care of it 1 year, moves on to the next one. And that's the approach he's done. And so, yeah, he didn't try to, I got to get this all done in 1 year. He took him several years.